Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, we will be discussing Introduction to AC Voltage Controllers as well as Single Phase Full Wave AC Voltage Controller with On-Off Control. And coming to introduction of AC voltage controllers, firstly, these AC voltage controllers are required in order to convert fixed AC to variable AC or otherwise variable AC to fixed AC depending upon the kind of applications, that is load requirement. And the examples of the loads of these particular AC voltage controllers are, we have induction motor loads, pumps, fans, furnaces, and blowers, lights, etc. These are the various examples of the applications of AC voltage controllers. And here, AC voltage controllers, as I told you, depending upon the application, it will supply either fixed AC, that is regulated constant AC, or otherwise variable AC if at all, if the input is fixed. Okay, it depends upon the application, kinds of the applications. And here we will be making use of SCAs in these particular AC voltage controllers in order to control the RMS value of the load voltage. And if at all, if input AC is varying, then some applications need regulated AC. In such applications, we will be making use of AC voltage controllers. And here, AC voltage controllers, it can either use phase angle control or otherwise it also uses on-off control. In on-off control, SCAs, the switches SCAs will be remain on for certain period of time and it will be off for certain period of time. That is, it is remain on for few cycles and it is remain off for other cycles. So that is how we actually we actually feed control output voltage to the load. And in phase angle control, by triggering the firing angle at the required instant, the required amount of the voltage will be fed to the load. So that is all about, we have both phase angle control as well as on-off control, either of these. And here AC voltage controllers are turned on by a gate drive and turned off by natural commutation. Natural commutation in the sense, since the input voltage is AC, the moment when supply voltage goes to 0, at that instant, since the after 0, it is passing through the negative half cycle, thyristor will be turned off naturally. That is called natural commutation. We don't need any external commutation circuits in order to turn off the SCAs over here. And in some applications, we can also make use of triacs instead of two anti-parallel SCAs. That is, we can replace the SCAs with triacs. And here, AC voltage controllers are of single phase or three phase type, and it can be unidirectional or bidirectional, but it can provide bidirectional control as well. Unidirectional in the sense, it is a half wave controller, and bidirectional control in the sense, it is full wave controller. Coming to the, let us first see single phase full wave AC voltage controller with on-off control. And here we'll be making use of, this is a basic AC voltage control circuit which has got two SCAs, that is thyristor 1 as well as thyristor 2. And here supply, main supply will be fed to the input of input to this particular SCAs, and this is connected to the required load. And as I told you, load can be induction motor drives or otherwise fans, pumps, blowers, lights, heating surfaces. It can be anything. So here we are making use of resistive load, and here we are making use of two SCAs which are actually connected in anti-parallel. And here, if you see, during the positive half cycle, here we are providing the triggering pulse for the thyristor 1. Here we are providing the triggering pulse for the thyristor 1 during the positive half cycle. Similarly, during the negative half cycle, here we are providing triggering pulse for the thyristor 2, that is IGT2. So, during the positive half cycle, whenever SCR is forward biased, that is here during the positive half cycle, due to these polarities, anode of the thyristor 1 is positive with respect to cathode. So what? T1 is forward bias, whereas T2 is reverse bias. It acts as off switch, and that is how current through the thyristor T1 starts flowing and then to load and back to supply. And in this particular on-off control, thyristor 1 is triggered at this instant called alpha is equal to 0 itself, and it is remained on for few cycles. As I told you, it will be remained on only for 2 cycles here. That is for, let us name it as n cycles. For n number of cycles, thyristors are remained on, and it is off for m number of cycles. So, by controlling the turn on and turn off time for certain period of cycles, we are actually providing the required voltage to the load. So, that is how we are actually controlling the load voltage. So, here at this instant called alpha is equal to 0, here we have provided the triggering pulse for the thyristor 1. So, what? Thyristor 1 is conducting current through the load, and that is how we are getting the output voltage, where V0 is equal to I0 into R. And later, during the negative half cycle has been appeared, and because of which the polarities will be changed now. And due to the negative half cycle, now the polarities will be here. It will be negative positive, such that thyristor 2 is forward biased now. That is, see, cathode of the thyristor 2 is more negative with respect to anode. That is how T2 is forward biased, whereas T1 is off. It is acting as an off switch now during the negative half cycle. So that is how T2 is started conducting current through the load in this direction. And if you see, at instant call alpha is equal to 0, we have provided the triggering pulse for the thyristor 2. That is how thyristor 2 is conducting during the negative half cycle till 2 pi. See, thyristor 1 has conducted till pi, and thyristor 2 is conducting from pi to 2 pi. And again, here we are providing triggering pulse for the thyristor 1, and again till 3 pi, T1 is conducting. And from here, during the negative half cycle, again T2 is forward bias. So what? T2 is conducting current right from 3 pi to 4 pi. And now the gate drive will be withdrawn, such that though the thyristors are forward biased during the positive as well as negative half cycle, it will not be able to conduct. So that is how we are actually controlling the output voltage, by providing triggering pulse for few cycles and again withdrawing triggering pulse for other few cycles. So that is the reason here the thyristors in AC voltage controller, it is remained on for n cycles and it is remained off for m cycles. So here, if you see, now the output voltage is 0 and again it is started conduction again from this instant when we provide the triggering pulse for the respective thyristors. And if you see, output current is just similar to that of the output voltage, because this is our resistive load. The output current waveform will be just similar to that of the output voltage. Only thing, magnitude will be reduced. Since I0 is equal to V0 by R, that is the reason magnitude will be reduced, or otherwise waveform is one and the same. So coming to the advantages, here advantages of single phase full wave controller with on-off control is SCRs are switched on at 0 crossings. So that is the reason here harmonics will be reduced. That is the advantage. And coming to the disadvantage, here if you see, the SCR are remained only on for few cycles, that is for n cycles, and remain off for m cycles. That means the voltage to the load is actually fed intermittently. So load should be able to sustain these variations. So that is the disadvantage associated with this kind of on-off control in AC voltage controllers. Coming to the derivation part, let us derive the expression for V0 RMS. V0 RMS, the general formula which we have is V0 RMS is equal to 1 by T, 0 to T, V0 square of omega T, d omega T whole to the power of 1 by 2. And here, if you check out the waveform, this is the waveform, and here coming to the time period part, if you see, every similar cycle is repeating for 2 pi. So that is the reason here the total time period will be considered as 2 pi. And it is actually conducting from 0 to 2 pi. And if you see, since this is on-off control, here SCRs are remained on for n number of cycles and remained off for m number of cycles. So that is the reason n, for which out of which it is remained on, and it is total time period is n plus m. So we will multiply it with n by n plus m, and here where V0 is equal to Vm square sine square omega T d omega T, since the waveform is sinusoidal in nature. And let us now, in order to integrate this term, let us bring out this Vm square outside. We get Vm square by 2 pi into n by n plus m. And in order to integrate sine square, let us write this in terms of 1 minus cos 2 omega T by 2, 0 to 2 pi d omega T whole to the power of 1 by 2. And we get Vm square by 2 pi n by n plus m. And let us take this 2 outside. Let me write it as 4 pi. And now integrating 1, we get omega T within the limits 0 to 2 pi minus integration of cos 2 omega T is sine 2 omega T by 2 within the limits 0 to 2 pi whole to the power of 1 by 2. And here, after substituting the limits, we get 2 pi minus 0 minus sine of 2 into 2 pi is sine 4 pi by 2 minus of minus plus, we get sine 0 by 2 whole to the power of 1 by 2. And here we get, after simplifying further, we get 2 pi, and this term is 0, this term is 0 whole to the power of 1 by 2. And here 2 gets cancelled, pi gets cancelled, so that we get Vm, by applying whole to the power of 1 by 2 to this term, we get Vm by root 2 under root n by n plus m, where Vm by root 2, we can write this as Vs, source voltage, Vs root over, let me write this term n by n plus m as K. So in this case, a single phase full wave controller V0 RMS expression is equal to Vs under root K, where Vs is source voltage and K is equal to n by n plus m. In the coming up lecture, we will be seeing single phase half wave rectifier. Thank you.